Hi everyone, welcome back to the second part of today's Oxford Discrete Maths and Probability seminar. So it's a huge pleasure to have a regular attender of the seminar speaking today. So Miklos Racz is going to talk to us about correlated stochastic block models. Over to you, Mickey. Thanks.
Yeah, thanks very much, Christina and Alex, for the organization. So it's a real pleasure to speak here. And I'll tell you about correlated stochastic block models, and in particular, two very natural statistical inference problems on them: graph matching and community recovery. So this is based on some joint works with Julia Gaudio, who's also at Northwestern, and my PhD student Anirudh at Princeton. And yeah, so perhaps if you were here about a month ago at the previous seminar, Jian Ding spoke about graph matching in random graphs and lots of exciting and recent progress. So there will be lots of overlap, or some overlap with the Jian's talk, but you'll also see that there are some differences, and I'll take a slightly different perspective to some of these problems. Okay, so let me get started. So first, I want to tell you about recovering communities and networks. So networks really play an important role in our lives, in society, in the sciences. And in a lot of networks, there are underlying communities. So these are kind of nodes that sort of have typically more edges between them than others. And so, for instance, in social networks, these are tight-knit communities, for instance, or in protein-protein interaction networks. These can be a collection of proteins which form a functional module. So these communities are often very important for the understanding the networks and their functioning. So it's a very important task is to be able to recover communities if you want to understand a network. So a lot of these networks are also very large in size. So this really leads to having to develop new algorithms and various statistical inference procedures to be able to recover the communities, especially because the signal to noise ratio present in these networks might be, it varies and might be small. So a natural approach to understand this question is to study probabilistic generative models, on which we can then naturally compare different algorithms and how well they perform. So for this, there's a very canonical probabilistic generative model for networks with underlying community structure. And this is the stochastic block model, which was introduced by Hahn, Lasky, and Leinhardt 40 years ago. So the model is very simple. So every node is drawn a community label at random, according to some probability distribution. So in this figure, these are represented by the different colors. And then given the community labels, every pair of nodes is connected independently with some probability, which only depends on the underlying community labels. Okay. And so this has been really well studied in several communities, such as in probability, statistics, physics, computer science, information theory, and so on. And so really, I cannot do justice to the huge literature on this topic, but here I've just collected some particular references from the past decade. So if you, in this model, perhaps the most important question is that of community recovery. So that is, if you're given the graph, without any community labels, just the graph itself, can we recover the communities? And there's different senses in which you can consider this question. You might want to recover the communities exactly, or almost exactly, or partially. Or the weakest notion is weak recovery or community detection, where all you want to do is just come up with a guess that is better than random. Okay. So in this talk, I'll focus on perhaps the simplest setting, which is when you have two balanced communities. So the setting is as follows. There's going to be n nodes. Each node, I, will have a community label sigma I, which is either +1 or -1. And these community labels are drawn IID uniformly at random. And then given the community labels sigma, then edges are drawn independently. If two nodes are in the same community, then it's drawn with probability P. And if they're in different communities, then it's drawn with probability Q. Okay, so this is the stochastic block model with parameters N, P, and Q. Any questions so far? And please feel free to interrupt anytime if you have questions. I won't monitor the chat, but feel free to just speak. Okay, so the stochastic block model is very well understood by now, and I'll discuss some aspects of this later in the talk. But what I want to focus on is something beyond the stochastic block model. So in particular, increasingly, we're interested in and have access to not just a single network, but multiple networks that are related in some fashion. So for instance, if we're interested in social networks, then there are lots of different online social networks that correspond to different interactions that we have in our lives. So for instance, Facebook is more about personal interactions. LinkedIn, on the other hand, is more about professional interactions. And of course, there's lots of connections between these two networks because, well, our personal and professional lives overlap a lot. So this means that these two networks really are correlated in some way. But at the same time, there's also differences in the two networks. So a general question is, how can we synthesize information from multiple correlated networks in order to develop better algorithms and better inference tasks for various problems? And in particular, in the talk, I'll focus on how we can better recover communities using multiple correlated networks. And let me mention that this perspective was already present in the pioneering early work by Holland, Lasky, and Leinhardt from 40 years ago in the first paper where they introduced the stochastic block model. So when they introduced the stochastic block model, they talked about a stochastic multigraph where there are M relations between the nodes. So of course, in the past decades, the main focus has been just on the graph setting. But of course, I think now that that is very well understood and we have much more data as well, it's the right time to understand this question with multiple networks considered. And I'll also mention some aspects that are quite important, which were not touched upon in the work of Holland et al. Okay, so to understand this question, we'll again turn to this perspective of considering a probabilistic generative model and understanding this question on such a model. So let me tell you about correlated stochastic block models. So the starting point is just a stochastic block model, as shown here. And we're going to focus on, again, just a simple two balanced community setting. So the two communities are those in red and those in blue. And okay, so this we can think of as a parent graph. This will become clear in a second why. So then what we can do is let's first subsample the edges of G with some probability S independently. So and to get the graph G1. So in other words, non-edges in G remain non-edges in G1. And some fraction of the edges of G are kept in G1. Okay. Now let's independently subsample G again a second time to get a second graph G2 prime. Okay. So now notice that both G1 and G2 prime have inherited both the node labels and the community labels from this parent graph G. Okay. So you can think of these two graphs as, say, Facebook and LinkedIn, if you wish. So what we're going to do one more step here, which is that we're going to uniformly randomly permute the node labels of the second graph to get, and so this uniform random permutation will be denoted by pi star, and we get the second graph G2. Okay, and really this models the fact that in practice often we don't know the underlying correspondence between the two sets of nodes. This can be due to all kinds of reasons. You know, it really depends on the application. But for instance, in the social network setting, maybe the social network is anonymized, or maybe you don't trust the node labels, and maybe they're corrupted, or maybe even you actually know the node labels, but you don't necessarily know how to match them into two graphs because they correspond to just different features of a person. Like I might use my nickname in a personal setting and my full name in a professional setting. Okay, so if two graphs G1 and G2 are generated in this way, then we say that they are correlated stochastic block models, and these are the four parameters here. N is just the number of nodes, P is the within community edge probability, Q is the between communities edge probability, and S is the subsampling probability. Any questions? Okay. So note that marginally both G1 and G2 are both stochastic block models, just because they are subsampled from this parent stochastic block model. And the parameters here are n, p times s, and q times s, and the multiplication with s is just because of the subsampling. But note also that if you look at the corresponding edges in the two graphs, then they are correlated since they're both subsampled from this parent graph. And let me go back to, again, this pioneering work of Holland, Lasky, and Leinhardt. So there, they look at G1 and G2 prime, and they call this a pair-dependent stochastic block model, and they actually study it in length in their original paper. So the main novelty here is considering the fact that we don't know the latent node correspondence. Okay. So then, the main question that we want to consider is, given two graphs generated in this way from the correlated stochastic block model, G1 and G2, when can we recover the communities? And here I'm mainly going to be focusing on exact community recovery. So in other words, we want to recover the partition of the nodes into two parts that corresponds to the two communities. Of course, there's no chance of getting the red and blue colors correct, but up to a universal flip of the colors, you want to get the partition correct. So in particular, this question is interesting if we can solve this in regimes where it's impossible to do so using only a single graph. So this will be the focus. Okay, now, before getting into this, I wanted to just tell you or refresh what we know about this question for a single stochastic block model. So if we want to recover the communities exactly, this partition between the two, between the nodes, then first of all, we cannot have isolated nodes. So we need to be we need to be above the connectivity threshold. So in other words, we need to be in at least a logarithmic degree regime. And in fact, the logarithmic degree regime is the most interesting for this question. So we'll focus on the setting where P is A times log n over n, and Q is B times log n over n. Okay, so from now on, A and B will be the kind of the main parameters that will go forward in the talk. So the question of exact community recovery was solved by Abe, Bandera, and Hall, and also Mostal, Nima, and Sly in 2014. And they showed that this is possible. And in fact, in polynomial time, in fact, in quasi-linear time, if this following condition holds, the square root of A minus the square root of B is greater in absolute value than the square root of 2. And I'll comment on this in just a second. And exact recovery is impossible if the inequality goes the other way. And for the purposes of this talk, let's not worry about the case of equality. Okay, so then this was by Abe and Sandin later understood this problem more generally for general stochastic block models. And I want to just give you the main intuition behind what this threshold is. So suppose that we're in kind of a Gini-aided setting where a Gini tells us all the node labels, all the community labels, except for a single node V. And then the question is to figure out, which community does this node V belong to? So if we know if we look at this node V, really the key information is how many neighbors it has in the different communities. And these will be binomial, but really in this regime, roughly Poisson, with a mean on the order of log n, with the precise constants depending on what the community label of V is. So in essence, the problem boils down to testing multivariate Poisson distributions. And in this logarithmic average degree regime, it turns out that you can characterize this problem, and the error probability will be some polynomial of n, and you can precisely characterize the error exponent, and it's given by the so-called Chernoff-Hellinger divergence. And what effectively you want is that this error probability be 1 over n, essentially, because you can think of essentially doing n of these tests for each of the n different nodes. Okay, and then when this Chernoff-Hellinger divergence is exactly equal to 1, that's exactly boils down to this condition here in the balanced two community case. Okay. So now let's go back to the setting of correlated block models. We know that marginally G1 is a block model. So we know exactly when exact community recovery is possible from G1. And it's possible under this condition. Here we have a square root of 2 over S on the right-hand side, just because the parameters are slightly different. Okay, so now how can we use two graphs to help us with community recovery? Now let's assume for a second that we know this underlying latent permutation pi star. So then what we could do is very simple. We could just take the union, we can just overlay the two graphs, take the union with respect to this matching and look at that graph. So here, if we look at these two graphs from the top, if we overlay them, then what we get is the following graph here at the bottom. And here we see different kinds of edges. So there's the green edges that are present in both G1 and G2. There's the yellow edges that are present in G1 but not in G2. And there are the pink edges which are present in G2 but not in G1. Okay, so there's some common information and there's some complementary information. And this union graph is also a stochastic block model, but with somewhat better parameters. So here you see this factor of 1 minus s squared. And this is simply just the probability that an edge in the parent graph survives in at least one of the subsampling procedures. Okay. So because this is also a block model, we know exactly when exact community recovery is possible. And it's possible under this condition. And this is a somewhat weaker condition than this first condition on the top, because we have better parameters for the block model. So in particular, this implies that if we knew the latent permutation pi star, and the parameters were such that we're in this regime here, then exact community recovery is possible from the two graphs combined, but it's impossible from just a single graph, G1. Okay. So this motivates the question of, well, this latent permutation is not known, so when can we recover the latent permutation pi star? And in particular, we're going to first focus on exact recovery. And here there are also different notions of recovering the latent permutation exactly, almost exactly, partially, or just weakly. And here I motivated this question through community recovery, but really this question, which is known as graph matching, is of significant independent interest. And Jian Ding's talk from a month ago was exactly about this, and he gave a really nice talk on all kinds of recent developments. And in particular, he also touched upon a lot of the application areas. So if you're interested in this more, I encourage you to watch his talk. It's on YouTube. So let me just say a few words about this. So the model of correlated Erdős-Rényi random graphs was first introduced by Pedersani and Grossglauser in 2011. And so that's exactly the same model that I just told you here, but just when P is equal to Q, so there's no communities. Okay. And so this has received a ton of interest in the past decade, especially in the past 5-6 years. And so both understanding fundamental information-theoretic limits for when we can recover the permutation and to what extent. And also a big question here is whether we can do this efficiently, algorithmically, in polynomial time. And so that has been a driver of a lot of these few works. And in particular, there have been some breakthroughs by Mao, Rudolphson, and Tikomirov, and also Mao, Wu, Xu, and Yu recently in the past couple of years that have achieved polynomial time algorithms for this ASCII under some conditions. Let me not go into this here, but again, let me refer you to Jian's talk where he describes a lot of this in great detail. Okay. Any questions? Good. I'll just continue, but please feel free to speak up at any time. Okay, so at this point, we have two main questions. The first is community recovery, and the second is graph matching. And both of these questions we want to answer in this correlated stochastic block model. And roughly speaking, the plan for the rest of the talk is that first, I'm going to fully answer the second question of graph matching, which then gives a partial answer to the first question of community recovery, and then we'll fully answer the first question of at least exact community recovery. Before I jump into that, I do want to still mention a few more strands of related literature. And these are strands of literature that kind of go beyond the stochastic block model to understand community recovery. And one main strand concerns multi-layer networks or multi-layer stochastic block models. So this includes the original work of Holland, Lasky, and Leinhardt, but many other works in the past decade. So here, they're conditioned on the communities. There are typically independent block models at different layers. So there are a couple of main differences compared to our setting. One is that the layers are typically not correlated, which they are in our setting, and also typically the node correspondence is known. So there's no issue of graph matching, which is a focus of our work. On the other hand, there's a line of work that considers contextual block models. So here, there's only a single graph, but the nodes have corresponding feature vectors that are correlated with the community membership. And there again, the question is, how can we integrate the information from the graph and the corresponding feature vectors in order to aid in community recovery? And there's a lot of very nice work in this context. And there's even a few works that kind of combine these strands of literature and synthesize them. Okay, so let me continue and let me tell you about some of our results. So first I want to tell you about graph matching, exact graph matching in the correlated stochastic block model. So this is joint work with Sridhar, who's my PhD student at Princeton. And so the result is as follows. So let's take, let pi hat be the following estimator. So you can consider this quantity, which is the alignment score. So if A and B are the adjacency matrices of the two graphs, and for any permutation pi, you can consider this quantity here, which is just, if you align the two graphs according to pi, how many edges are present in both. So that's this alignment score. And pi hat is just the permutation that maximizes the alignment score. So this is a very natural estimator. In fact, in many problems of graph matching, where there's, for instance, no underlying probabilistic generative model, this is the quantity that is, this is the function that is, objective function that is optimized. You know, in many applied settings, you know, graph matching is equivalent or is considered the problem of maximizing this objective function. Okay, so then with this estimator, if s squared times a plus b over 2 is greater than 1, then this estimator is correct. It's equal to the true latent permutation pi star with high probability. So with probability tending to 1 as n goes infinity. So let me say a few things about this result. So first of all, this pi hat is, as I said, a very natural estimator. It's in fact the maximum a posteriori estimator for the correlated heterogeneity model when a is equal to b. In general, for the block model, it's not the map estimator, but it's close and it still works just as well. So this result for the heterogeneity setting was proved by Kulina and Kiavash, so when a is equal to b. And also Wu, Xu, and Yu, they studied this question further, and especially in the dense regime, there's further intricacies. But here we're focusing again on this logarithmic average degree regime. So what is this condition? So this is nothing else. So if we consider the two graphs and we look at the true latent correspondence and consider the edges that are present in both graphs, so that's what's known as the intersection graph. And recall that we're in the logarithmic average degree setting. So this is simply, the average degree is simply this times log n. So this condition is simply that the intersection graph is connected. So this is simply the connectivity threshold for the intersection graph. So previously, Honora and Garg and Erkip proved the same conclusion, but under stronger parameter assumptions, and also assuming that all community labels are known, which is an issue for two reasons. Well, one, if we want to use this for the downstream task of recovering communities, then it's not so useful. But also, if you assume that all community labels are known, that kind of the proof kind of reduces to the Eiderstring setting. So in some sense, the main difficulty in the proof is to deal with the community labels. Okay, so this result is tight. So if you're above the connectivity threshold for the intersection graph, then you won't be able to exactly recover the latent permutation. So let me just, so this is a previous result by Kulina, Singhal, Kiavash, and Vital. So this is the easier of the results. Let me just explain quickly why this is so. So again, this condition is that the intersection graph is disconnected with high probability. And in fact, under this condition, the intersection graph will have many isolated vertices. So what's an isolated vertex in the intersection graph? It means that it has some edges in one of the graphs in G1 and some edges in G2, but these don't overlap at all. So in some sense, there's no shared information, and this makes it hard to classify such vertices. Okay. Any questions? Okay. So that's graph matching. So let's see how this then, what this shows for exact community recovery in the correlated block model. So under these two conditions, exact community recovery is possible. And well, we've already seen the proof of this result. So under this first condition, we've just seen that we can recover the latent vertex permutation pi star. And then we can just overlay the two graphs and use any community recovery algorithm that works down to the threshold. And this is the precise condition for that. And the second condition is also necessary. So if we don't have, if this inequality goes the other way, then exact community recovery is impossible. So this proof is again simple. Here we can just give the latent permutation to the estimator, and it's still impossible to recover the communities from the correctly matched union graph. Okay, so this slide is maybe a bit of a mouthful, so it's easier to look at some phase diagrams. So let's look at, in particular, this one on the left. So there's three parameters here, A, B, and S. S is the subsampling probability. So let's set S to be equal to 0.25. That's this plot on the left. And the two axes are A and B, respectively. And so there are four regions here. So first, in the green region, you can just exactly recover the communities from G1. So that's well understood. In the red region, you cannot do so, even if you have both of the two graphs. Now, there's the cyan region. In the cyan region, you cannot recover the communities exactly from G1, but you can recover the latent permutation. And after that, you can also recover the communities exactly from the two graphs. And what I haven't told you so far is this yellow region. And this is where exact community recovery is impossible from G1. It's also impossible to recover the latent permutation exactly, but it still might be possible to recover the communities by combining information from the two graphs. Okay. So, yeah, let me just very briefly say a few words about the proof for graph matching. I won't say much. Okay. So the first thing is, you want to understand permutations on the nodes, but really in this objective function for the alignment score, you want that it corresponds to permutations on the vertex pairs. So there's a one-to-one correspondence. And then what you want to understand is the alignment score of some permutation tau on the vertex pairs and how that compares to the true alignment score. And we want this true alignment score to be the largest, and that's when the estimator succeeds. Okay, so effectively, without going into all the details, effectively there's two competing forces. There are some permutations that are relatively close to the truth, but and they have a higher chance of becoming, having a higher alignment score than the true permutation. But there's relatively few of them. And then there's many permutations that are far from the true underlying permutation. But there's only but the probability that such a permutation will end up having a higher alignment score than the true latent permutation is much smaller. So these are kind of the two competing forces. And let me not go into the details, but roughly, from the first competing factor of how many permutations are there at a particular distance, that gives a polynomial factor from a union bound. And then for the other factor, what you really have to do is you have to do a kind of large deviation type of calculation in order to estimate the probability that a given permutation that is at a particular distance from the true permutation will have a higher alignment score. So it boils down to understanding various generating functions. Without going into the details, let me just mention a few key aspects. One is that the independence in the edge generation in the underlying model leads to the fact that here, if you decompose the permutation across cycles, then you have independence across cycles. So that's a very nice aspect of what's going on. And for correlated heterogeneity, in the correlated heterogeneity case, you even have explicit formulas for these generating functions for a cycle. So that's no longer the case for the block model. And so this is where kind of the main technical difficulty comes in. So here we just developed some kind of recursive bounds as you go along the cycle for such generating functions. So I think in the interest of time, I won't say more, but I'm happy to chat more about this offline. So next, I want to touch upon that yellow region in that phase diagram that I haven't told you about yet. And so here we'll really see the interplay between these two inference problems, because so far we just used community recovery algorithms as a black box, but now let's see how these two things interplay. So in this yellow region that I mentioned before, so just to recap, we can't exactly recover the communities from a single graph, and we also cannot recover the permutation exactly. But is it possible that we can still recover the communities exactly by combining information from the two graphs? So we characterized the answer to this question in joint work with Julia Gaudio and Sridhar. So the answer is that in part of this yellow region, you can do it, and in part of it, you can't. So in this picture, in the dark blue region, you actually can recover the communities exactly, while in this pink region here, you cannot do so. So the curve that separates the pink and the dark blue regions is given by this equation here, where there are two terms. So there first is this s squared times a plus b over 2 term, which is familiar from just the conductivity threshold, which characterizes when exact graph matching is possible. And there's also this second term, which is s times 1 minus s times, well, this quantity here, which is just, this is really just the Chernoff-Hellinger divergence that characterizes exact community recovery. So here, in that previous threshold that you might have seen on the slide, several slides before, that threshold is just rearranged into this formula here. So in other words, this threshold has a nice form because it really captures the interplay between the graph matching and the community recovery tasks in a clean way. Okay, any questions about this? Okay, and again, there's this first condition over here, that's just saying that we're not in the red region. Okay, and once we're not in the red region, this equation describes the curve that separates the dark blue and the pink regions. Okay, so yes, so let me again maybe show some more phase diagrams. So perhaps one more comment here is that in this pink region, we can't recover the communities exactly, even though so this were possible if the latent permutation pi star were known. So here in this pink region, really the bottleneck to recovering the communities is not knowing the permutation well enough. Okay, so let me try to describe to you at a high level the algorithm of how we can recover the communities exactly in that dark blue region. So first of all, we're going to start by a community recovery algorithm on just a single graph G1 that almost exactly recovers the communities. So it won't do so exactly, but almost exactly. And we're going to use an algorithm of Moslany and Sly. And but we also, because it's impossible to recover the communities exactly from just a single graph, so we have to combine information for the two graphs. So what we're going to do is we're going to come up with a matching, which is a partial matching. So we're only going to match a subset of the nodes, but this will match almost all of the nodes. And it goes as follows. So this is known as the K-core estimator. So it goes as follows. So for any permutation, any matching, you can look at the intersection graph and then look at the K-core for a particular K and look at its size. And the K-core estimator simply chooses the permutation that maximizes the size of the K-core of the intersection graph. Okay, so we're going to choose a particular K. In fact, we choose K equals 13, but think of K as just some reasonably small constant. And that's what we're going to look at the K-core estimator. So the K-core estimator has a couple of, and I should say that the K-core estimator only matches the nodes that are in the K-core of the intersection graph. And for the other nodes that are not, it just doesn't say anything about the match. So the K-core estimator, so this was introduced for the Erdős setting by Kulina, Kiavash, Mittal, and Poor. And it has a couple of nice properties that I want to highlight. The first thing is that so you can show that with high probability, all of the matches that it makes are actually correct. So it doesn't make any false matches. The other nice property is that the number of unmatched nodes is essentially optimal. So in this case, the number of unmatched nodes will be n to this power 1 minus s squared times a plus b over 2, which is plus a little one factor that I've left out here, which is essentially the same as the number of isolated nodes in the intersection graph. So you can't really do better than this. So these two aspects about the K-core estimator are nice. Now, and the first aspect that it's correct, that it doesn't make any false matches, is particularly useful for when we want to use such a matching for downstream estimation tasks, such as community recovery in this case. Now, I should add that these first two bullet points here, really these are not in order. These are just can be done in parallel. So the second point has nothing to do with the first point. Okay, let me quickly remark as an aside that this K-core estimator works actually well for more broadly, not just for Erdős and for correlated block models, but more broadly for correlated inhomogeneous random graphs. So we have a recent work with Ani from a month ago where we explored this for a broader class of models. And I should also mention that this is quite closely related to the densest subgraph estimator, which Jian and Hangdu were focusing on in a couple of very nice recent works, where they closed some constant factors in the information theory limits for graph matching for Erdős. And it's closely related because, well, if you look at the k-core there, that's kind of a condition where you want all of the degrees of the subgraph to be at least k. Whereas in the densest subgraph, you want kind of the average degree of the subgraph to be large. So these are kind of, in some sense, incomparable, but both have positive features that can be used for different reasons, depending on what you're interested in. So I can comment more on that if anyone is interested. Okay, but let me go back to this algorithm where we want to do community recovery. So now we have an initial guess for the community labels from the first point. We also have a partial matching of the nodes, and this matching is denoted by mu hat. So now what are we going to do? So actually, we're going to actually slightly modify this matching for technical reasons, and I'll explain why in a second. But okay, so here's what we're going to do. For the match nodes in G1 that have a match in G2, what we're going to do is we're just going to look at the subgraph in G2 and take the union of these two subgraphs. And now we have a larger graph with more signal. And we're simply just going to use a majority vote among the neighbors. So for every node, we just look at the neighbors in this union graph and take a majority vote of the preliminary labels, community labels, and that will be its final estimate for this community label. And so why will this work? There's a couple of, so first of all, we're not in that red region. And it turns out that once we're out of that red region, if we could actually combine the two graphs without any error, then it turns out that every node does have, among its neighbors, the community label is the majority. So the majority among its neighbors' community labels is the same as its own community label. So this is true for every node with high probability. Now here there are a couple of subtleties. One is that, well, initially not all community labels are correct. So what we have to make sure is that kind of the incorrectly labeled nodes are not well connected. And it turns out that this is a geometric property that can be shown, and it's it does hold true for this algorithm by Moslany, and Tsai. The second aspect is that, well, here we don't have all the nodes, we only have a subset of the nodes because we've thrown out the unmatched nodes. So we cannot have a node that we're considering here to have many edges to the unmatched nodes. So we want to make sure that that's the case. So that's where we we expand the set of unmatched nodes using a technique of Wuchak, just by a constant factor. But then after that, we have that every node here that we care about has only at most one edge to the unmatched nodes. Okay, so that's the estimator for the community labels for the matched nodes in G1. And what do we do for the unmatched nodes? Well, for the matched nodes already have a fixed community label, and hopefully this is correct. And so what we just do is for every unmatched node, we look at its neighbors in G1 and just use a majority vote. Okay. So it turns out that this is again one of these testing multivariate Poisson hypothesis testing problem. So the relevant quantity is this Chernoff-Hellinger divergence with this factor of s times 1 minus s. The s is perhaps natural just because G1 was subsampled from the parent graph. And the 1 minus s factor is really because we're considering unmatched nodes. And so now we have this quantity, and the number of unmatched nodes is not n, but it's n to this power here. And so if you combine these two, that's where this threshold comes from. Any questions? Okay. So let me continue. Let me just briefly sketch the impossibility argument. So here, let's consider this singletons in the intersection graph. And in the regime we're considering, there's going to be polynomially many singletons in the intersection graph. And so it turns out that you can give lots of extra information to the map estimator So you can give it all. So suppose we want to figure out the community labels in G1. Let's give it all the community labels in G2. Let's give it the single set of singletons in the intersection graph. And let's give it all of the true permutation outside of the singletons. And the estimator will still fail on these singletons of the intersection graph. And so the proof uses a careful second moment analysis, although there's no real tricks necessary. Just do it carefully. Okay, so at the end, let me touch upon some open problems and future directions. So one main question is efficient algorithms. So the algorithms that I told you about are not efficient. In particular, computing the alignment score is not efficient, although in the independent case, Jan mentioned last time that he has some results for essentially a p-task in the independent case, but not in the correlated case. And then also the k-core estimator that I just told you about, that's also, we don't have an efficient way to compute that. So, well, do we have efficient algorithms for in the regimes that we're interested in here? All the community recovery steps, those are efficient and no problem, at least in this setting of two balanced communities. And so, as I mentioned before, there have been some very exciting developments for efficient graph matching in the correlated heterogeneity setting. So these have been some real breakthroughs, and I hope that this can spur further work in this area, and for broader classic models, in particular the block model. So in this talk, I focused on exact community recovery, but we can go and try to understand this question in sparser regimes where the question is harder, but in principle, more information. So combining two networks should help in all of the other regimes as well. So in particular, if we look at almost exact recovery, can we have improved error rate? For partial recovery, can we improve the fraction of nodes for which we can recover the community labels? And community detection, where we just want something better than a random guess, will the threshold change and become lower? And so we're working on some of these questions. So with Julia and Annie, we are working on, and hopefully, if all the technical things work out, we've figured out kind of what is the optimal error rate for almost exact recovery. And also in the constant average degree regime. So there's this celebrated Kesten-Stigum threshold that describes the threshold for when community detection is possible from a stochastic block model. And so here there should be a regime where both correlated block models are below the Kesten-Stigum threshold, yet it is possible to combine information from the two to do community detection. Kind of going beyond that, of course, we would like to try to understand what is the new threshold, what is the threshold for community detection from two correlated block models, and that's something that requires, that it's not even clear how to get a guess for what this threshold is. Certainly, this will, I believe, will need even advances even in the setting. We'll need to answer questions that are even unknown in the correlated heterogeneity setting. So for instance, if you can do partial recovery, what of the latent permutation, what fraction of the latent permutation can you recover correctly? That's something that is not yet known for heterogeneity. And really, the challenge in all of these is that you really have to understand the interplay between these two inference problems. You can't just study them alone. So of course, all that I said was focused on two balanced communities, but you can consider this for general block models with K communities, general parameters, etc. So there's lots of variations on this question that you can consider. Okay, let me end here. So just to summarize, I told you about correlated block models and the fundamental limits of exact graph matching and exact community recovery. In particular, we showed some regimes where exact community recovery is possible, even when you can't do it from one graph and you can't recover the latent permutation exactly. And just broadly speaking, I think correlated random graphs present many challenges and applications, and I hope that this talk and also previously Jan's talk has convinced you of this. Thanks.
Thanks, Mickey, for a lovely talk. I'm about to invite people to ask questions, but I'm going to use my privilege as chair to ask one myself.
Sure, yeah.
So this k-core matching algorithm seems really powerful and, as you said, useful in different places. So it's sort of a naive question, what's k? Which k is useful?
Yeah, so you can, I think even just, a constant k where even, I think as you're going into denser regimes, you need to choose k to be larger. But even so, for instance, in this recent paper with Ani, we look at up to like square root of n average degree, like from sparse up to there. And in all those regimes, the constant k suffices, but you have to increase k with the power of the n. And yeah, there's something going on at square root of n average degree. So that's something we need to understand better. But yeah, so a relatively small k should suffice.
Great, thank you. I think Alex has a question.
Yeah, so nice talk. So you've been talking about two. So in this correlated model, you've got two samples.
Yeah.
So do you know what would happen if you were allowed to take many samples, so thousands of examples? So. Yeah.
No, I think that's a really great question. I think the red, then first of all, there's many different models in which a vector of bits can be correlated. I think this parent graph thing is not the right model in that setting, because then you're kind of limited by whatever, the best you can do is just take the union and then you do whatever you have for the parent graph. So I think the better model in that case is that you just have like a common part and plus an independent part for each of the other graphs, right? I think that's the better model in that case. And yeah, I think it's a very interesting. I mean, it's certainly a question that I plan on thinking about. In principle, you could have some setting where maybe you can do absolutely nothing from each of the individual graphs, but if you take log n of them, then you can do just everything, right? And that would be very cool.
Okay, thanks.
I've got a question or two. Is there any significance to the sort of last curve when it goes into the red region, if you see what I mean? Is there like a boundary where you can identify the vertex types but not which vertex is which, or I don't know? Would it mean anything?
Oh, sorry. Let me go back to the so let me 1 second. Yes, so absolutely. When you want to understand optimal error rates, then that's exactly what you want to. It's important, yeah. So essentially, that when that curve goes into the red region, it's telling you which part of which inference problem is the bottleneck. So in particular, I mean, it's not clear, but this line here, this vertical line here, that's where this curve goes to the midpoint of that line, and there's an intersection point here. And so effectively, in this red region, you can't exactly recover the communities, but a natural thing is you can do almost exact recovery, and you want to understand what is the optimal error rate. And essentially, there's going to be two regimes, and here in kind of the pink intersection red, the recovering the permutation is the limiting factor, and here in this region outside, recovering the communities will be the limiting factor. Yeah, absolutely.
The other thing was about the sparse thing. So,
yes.
so you mentioned you're working on that. Is that going down to really sparse? So like constant average degree, and then you want to know how many vertices you get wrong in terms of as a function of that constant. Or, I mean, what fraction of vertices you get wrong as a function of that constant?
Yeah, that would be great. So I mean, what we want to do first is to just look at the constant but very large average degree. Just because
Yeah, I think that's.
if the average degree is constant but very large, then at least for the permutation, you can recover like a 1 minus epsilon fraction of the permutation, where epsilon is like a constant. It's constant but can be made arbitrarily small.
It should be like exponentially small in the average degree, you hope, or something.
Right. So yeah, the hope is that, you know, at least in that regime.
Yeah, that's what I meant, I think.
Yeah. So beyond that, it would be great to understand it for smaller constant average degree, but that's the first step. Yeah.
One more quick question.
Yes.
Is S always constant, or is it interesting to look at S going to 0? That's a sort of trade-off between S and P.
Yeah, we've always focused on S constant. Certainly, it is interesting to look at smaller S. In fact, in a lot of the literature on correlated edge-correlated, people have looked at definitely smaller S going to 0 as well. And it's also interesting to understand S close to 1. S equal to 1 being essentially just kind of graph isomorphism. And in, you know, a lot of the algorithmic works, first there were improvements when S is 1 minus little o of 1, and getting algorithmic results for increasingly larger little o of 1. And then eventually there were these couple of breakthrough works that I mentioned that achieved efficient algorithms for correlation S that is bounded away from 1. And the second one even has kind of there's likely an information computation gap in this question, where S squared is equal to 1 over alpha, or S squared is equal to alpha, where alpha is this Otter's constant. That shows up, and that's some kind of computational boundary.